Hello community, let's talk about the latest technology with GraphRAG when we implement multi-agent system. So imagine a world where AI system would really reason and with the depth of a Sherlock Holmes, and it would explore options like a chess grandmaster, and we would have multiple agents that work together and reason together like a Navy SEALs team. And you would ask, what is holding us back? And the answer might surprise you because it is the complexity of reasoning itself. Today we want to find two brand new solutions from a technical perspective. We will defragment and redesign our knowledge graph, plus we will design a new improved Monte Carlo tree search methodology for a new multi-agent creation, recruitment and communication strategy that will adapt inherently to the complexity of my task. Let's open up the session and here we go. Now, if you're not really absolutely sure about GraphRAG system, Graph Retrieval Augmentation RAG, January 21st, 2025, this is the study I would recommend from you, the Hong Kong Polytech University. A beautiful study. You have here the GitHub repo, you have the open source data, the project, the code, the research paper, you have everything that you need. Just look here at the beauty that they did here to collect here all the different GraphRAG system up to January 2025. If you are really not sure about the traditional RAG implementation and what a GraphRAG implementation brings you, here you have 5 beautiful points that will show you how much better a GraphRAG implementation is. I personally have implemented about 36 different GraphRAGs, but look at this. This is a taxonomy for GraphRAG for customized LLM. And here you can dive into and enjoy whatever methodology you like for your particular topic, for your particular domain expertise. What is really nice is this one here, I think. Here at the top, we have a non-GraphRAG system, how it works. Then we construct here some customized knowledge graphs of our data. And then we do the indexing with graph. And the indexing with graph is really nice. If you're not familiar, index-based GraphRAG systems summarize the corpus into high-level topics, which are linked here to form an index graph, while fact linking maps here the different topics to the text. We have a 2-layer structure, which has a real good performance. Please remember index-based GraphRAG system, because we will use them in 5 minutes times. Look at this, isn't this beautiful? Here you have on one look, you see retrieval techniques, similarity-based, logical-based, GNN-based, LLM-based, reinforcement learning-based. You have the input query side, graph side, the graph pre-processing, the matching for the implementation, the pruning methodologies that are used, and the output form that we need. Please notice that we have the Monte Carlo tree search implementation here. And yes, we're going to talk about this in 30 seconds. If you prefer video, I have here Empower LLM with knowledge graphs here from MIT. This video is here LLM plan on graph or knowledge graph adaptive reasoning. And if you really want to have 5 methods for knowledge-driven RAG system here, including the brand new SimGraphRAG methodology, this is the video for you. But now we need a spark that will ignite our ideas. So let's start here. We need a new system. We need a new AI system that's teaching our LLMs to become more strategic, as an architect. And we will implement this with a new Monte Carlo tree search implementation that it is called Master. And this Master implementation will be implemented on a multi-agent system with a self-evaluation function that is brand new. Let's have a look. But architecture needs context, especially in the case of AI. So for LLMs to truly reason here deeply, they navigate here vast oceans of knowledge. And this brings us to our second new AI preprint, Fast Sync Graph. Yes, we're going to talk about 2 publications I've chosen that were published today, but they fit perfectly together, and I will explain in a moment why. So we have our Monte Carlo tree search master. This is about strategic architecture to explore here our complete solution space. And then this fast thinking on graph is becoming now this master cartographer of a knowledge graph to chart here smarter pathways on our knowledge graph for the LLMs to explore and reason on those knowledge graph pathways faster, cheaper, and have a better performance. So what we do, We design new tools for our job on knowledge graph, and we will design new knowledge spaces to work in. So we really remodel here the complete environment. Let's come to the core elements of this video. And you know, if you work with Monte Carlo tree search algorithm, you know we use them primarily in AI to augment the planning capacity of our LLMs. But we encounter problems because this Monte Carlo tree search relies heavily on extensive sampling simulation, and we need them to approximate the true reward distribution, and this brings us to two problems. At first, it works great. Monte Carlo tree search is beautiful if you have a game like Go, where you have an objective reward, a 1 for a win and a 0 for a loss. However, if we have question and answering, logical explanation, reasoning task, the result of all this simulation here is simply an answer to a question. And here we cannot obtain an objective reward without knowing here the ground truth. And we have access to independent sources that are really 100% correct. And secondly, we need here simulations exceeding a minimum 30 simulation, so we have excessive token usage. It's really expensive, takes really a long time. So is there a way to circumvent this here? Yeah, of course. Let's talk about the new idea. Multi-agent system with tactical execution and reasoning using LLM specialized Monte Carlo tree search master. The goal is simple: autonomously adjust the number of agents that we need for a task, given also the complexity of this task, and ensure here a focused communication among the perfect number of agents. So let's do this. Nothing is easier. And the authors decided we start by eliminating the complete simulation process in Monte Carlo tree search. And you might say, how is this possible? How should this work at all? And they say, hey, you know what? We have an idea. We just take an additional step here in the Monte Carlo tree search cookbook. And this step is introduced for the LLM to provide here more context before the self-evaluation process starts. And then the LLM's confidence that we need the scoring function is incorporated here as a weight for the reward to regulate here the influence. And of course, we have our backprop mechanisms. Great. And you know what's interesting? You know what's fascinating? If we introduce this novel agent system, we now optimize the creation and the interaction of agents. And this brings us to a complete novel multi-agent system. Let me explain. So we have child agents, and they respond to and build upon the outputs from the parent agent, making here the recruitment and communication more manageable and more efficient and beautiful. And this scales dynamically with the number of agents based on the task complexity and ensures our flexibility, and everything is beautiful. But let's come to the fact. This is now a new chapter. And we have here the main publication, January 24, 2025, a multi-agent system with LLM specialized Monte Carlo tree search that we do have to modify. Because, as I told you, the environment doesn't provide here an objective feedback for complex causal reasoning. If we have here complex human sentences, we can't decide it's a 1 or it's a 0. So we have to address this limitation here in the Monte Carlo tree search. And at first, it looks like everything the normal way we do it. No? We have our root agent and we have our child agents, and then we generate here down step by step. We calculate here the upper confident bound here on the tree, the UCT. And then if we find somewhere deep here the correct answer, we just back propagate here, and the UCT value on the correct pathway is increased. And so we know here this is a beautiful exploitation path. And if you want to see this in a little bit more detail, you see this here on the right-hand side. But what are all those terms? We have to look at them in detail. So let's start with the flow that's working here. We have a root agent with my query. And the agent then prompts the LLM to produce a verbal sort reflecting the current reasoning trace and to propose an action to solve the problem. The agent consequently then executes this action by tool use function calling and interact with the external environment, providing here feedback, what we call observation. So then we have produced sorts, actions, and observation, and this forms together the solution, what we call here in this paper, the solution of the agent. Next step, the agent invokes now the LLM to generate here a textual output that validates now the key facts in this solution. We have the complete validation phase. Finally, the agent prompts now the LLM to assess the progress made towards solving here my query, producing now a specific score and the LLM's confidence in this. And this is now what we call together an assessment. And these two values are then extracted, the score and the confidence, forming the assessment. And all of this together, the solution, here's the solution, the validation, and the assessment, they constitute now the context of the agent and are stored in its memory if we only have one agent. So the score serves here as the initial reward for this single agent. But now we can go with this idea, multi-agent. Look at this, if we have a parent agent and then you immediately understand here the sort, the action, observation, validation, assessment, evaluation phase. Now you know what's happening here. And after we have this now with the root agent we just described, now we create child agents. And they follow here absolutely the same procedure with the root agent's context appended to the prompts of these child agents, as they need to continue solving now our problem. Well, of course, but you know what? Empowering here the LLM to judge the quality of its own reasoning step is here the crucial step. So we say, hey, we have this LLM and this LLM is beautiful. So why not give the LLM also here the power to judge its own reasoning step? Because whatever the LLM is going to hallucinate or has a knowledge of, or we have fine-tuned on a particular domain knowledge, we want this domain-specific LLM to judge the quality of the reasoning step given the domain facts. So we use here the LLM. Now, if you look at it a little bit more on the mathematical side, hey, this is beautiful because here our original for the classical Monte Carlo tree search, our UCT formula is here this one. And you notice simply two terms, where the first term, our Q sub I, is here simply the estimation here of the quality value. It represents here the average reward from the simulations. N sub I is here the total number of simulations by the parent node of the current node. Beautiful. But we are much more interested here in the second term, no? Because you remember from our other videos that here our UCT balances here exploitation and exploration. And this here is our exploration term that favors now the nodes in our knowledge graph that have already fewer simulations done. So these are the nodes that are not as prominent or we simply forgot. So therefore we want to make sure, hey, if we calculate this, we have to go really all the nodes. We have to find all the nodes hidden somewhere in the corner of our exploration space. And this is such a simple formula. And this is the original formula by the original Monte Carlo tree search. And now we just have to modify this a little tiny bit. And this is done immediately. Remember, we have an initial reward and an updated reward. And the initial reward is extracted from the assessment when this agent is generated. And the updating reward is the mean of the rewards from the backpropagation. So we have those figures. Now our quality is now simple here. First term and then the second term. So we modify here the reward estimation. And we have here at first, C sub init is here the confidence of the LLM to this initial reward, where R sub init is here the initial reward given by the LLM itself and our classical formula. So if we take everything together, here we have it now. This is now Monte Carlo tree search, the master UCT, the new formula that we built. 1, 2, 3 terms. If you compare this, this normative factor here, 1/10 here, never mind, this is just here a factor that was found to work beautifully. Don't care about this factor. And if you compare this here to a classical UCT formula, you see immediately, yes, we are familiar here with the exploration term. Great. Yeah, a little detail. Just note the number of the backpropagation in our system is now significantly lower than the original Monte Carlo tree search. And this is beautiful because it's now even faster, even more faster, while the slope of the logarithmic function is here relatively steep when our variables are small. So the value of the exploration term becomes now the dominant one. So remember, we have now an additional validation step, of course. So before assigning now the reward in the assessment phase, this additional validation step is to be conducted. And simply where the LLM comments here on the correctness of the facts in the current solution. And these comments are added to the prompt for the assessment step, guiding here the LLM towards a more reliable reward. So beautiful, and we notice that the LLMs performs better when it is asked to address only one problem at a time, and this is here the beauty of chain of thought idea, no? And you might say, hey, wait a minute, the correctness of the facts? This sounds so familiar, no? Yes, of course. And there's a special bonus, because if you have seen my last video, and I was talking about the ultimate fact-checking AI machine by Johns Hopkins and Stanford, we looked exactly at fact decomposition and fact decontextualization. If we perform this in tandem, we got, and this is a work here by Johns Hopkins University from mid of December 2024, we have now the perfect machine for the factual verification in long-form text generation by our AI systems. So great, but there's another fact. Yes, of course, we were talking about GraphRAG system and optimization and defragmentation here of the reasoning space. So let's do this now. So just as a definition, graph-based RAG system widely considered an advanced RAG system, since we're incorporating here our knowledge graph as an external data source, information source for our LLMs to communicate, to reason, whatever. And now we look at a brand new GraphRAG paradigm, and this is called fast thinking on graph. The main idea is so simple, you're not going to believe this. We have now we move from node to node. We think now about community by community on our knowledge graph. So, and this unbelievable, I will show you how we do this. It will improve the accuracy of the answers generated by our LLMs, but it will also enhance the efficiency of the complete RAG system. And you might say, hey, why has this not been invented before? I can't tell you, but it is so nice. So forget of getting lost here in the noise of individual node to node or whatever. We build now neighborhoods on our knowledge graph, semantic neighborhoods that are maybe query related. And you know what? There's a kicker, because it doesn't just stop at finding here and building here the semantic communities on our knowledge graph manifold, but it also prunes out here the irrelevant ones, making it even more faster and more efficient for our reasoning process. So what we end up with? Higher accuracy, faster answer, and then an AI system that can explain its reasoning like never before, with such easy methods and ideas. And here's the paper for this. This is from January 24, 2025. For me, just 2 days ago. This is here from the School of Cyberspace Security, Beijing University of Posts and Telecommunications. Hello, colleagues. It's a beautiful paper, and here you find the code. I often ask, hey, where is the code? This is always here the link to the code, the GitHub provided by the authors, and this is the best code resource for this particular problem. Great. So what it does, this fast thinking on graph, it really rewrites the rules for the reasoning if we work here with vast knowledge graph, huge knowledge graph, million of edges and nodes and whatever. So it enables now our AI to extract meaningful insights from the interconnected webs of the data by focusing on communities of relationship. And this is such an elegant approach that's both faster and smarter than everything else we have done before. 2 simple phases. At first, we have to start. We identify here a starting community and use here a local community search to simply detect neighboring communities, semantic communities that are real close to our starting communities. And then in the reasoning phase, you know what we do? We apply a Monte Carlo tree search, and we have here a modified upper Coverton bound for the trees formula. And you say, this sounds so familiar. Yes, of course. And this was the reason why I've chosen from dozens of new papers that came out today those 2 particular papers, because they work beautifully together. The authors have no idea that I use them here in tandem, but those 2 papers, they are just, they are just perfect for each other. Great. So what do we do? We have, of course, to convert then the graph structure into the textual input for our LLM. So we have our community to text methodologies, and we will use here, I will show you an example in graph to text. However, please note there's a problem. This graph-to-text is not perfect yet. So this can really introduce hallucination, especially if you're working with larger communities. If you have real technical terms, real technical interlinks on our knowledge graph. So there is now really a chance that hallucination will be generated by this graph of text. However, this thing now significantly outperforms the traditional RAG system and all the other graph-based approaches if we have multiple datasets. So really, this fast thinking on graph achieves a higher accuracy, a faster reasoning, and a better explainability compared to the previous methods. At least this is what the authors claim. And you know what? I think this is fascinating because in both studies I found the core element, and this is structure. You don't just need more compute power. You can do it also in a clever way. And here I think the success of this fast thinking on graph is that structured knowledge graph, refragmented, redesigned knowledge graph can significantly enhance the reasoning capabilities of our LLMs, especially if we have complex query like in scientific application. Plus, this community-based approach reduces here the reasoning chain length, and this is crucial for the efficiencies and really large-scale application. It is cheaper, it is faster, it improves, go with this. Just a shorter reminder, we only have 3 elements in this idea, no? We just have a local community search algorithm to find here the local community around us when we start somewhere on the knowledge manifold. Then we have a 2-stage pruning process, I'm going to show you in 10 seconds, that simply eliminates irrelevant information to my specific query that I have as a user. And then we have a community-to-text conversion method, simply to bridge the gap between a graph triplet visualization and here a human language. If you want to see this in images, beautiful. So we start here, we have a community detection on subgraphs, then we have a 2-step pruning process, a modularity-based coarse pruning, and then the LLM-based fine pruning. The LLM decides here, and then we have the perfect reasoning. But what I want to show you here is a notation. If you read the study, you find a notation, and I have to explain this to you. So we have a 1W, 1D system. So one wide, one deep system focuses on reasoning about one node and its immediate one hop neighbor. So one node wide and one system step deep. So only one hop. So only one hop from one node to really the next node. Then we have an NW 1D system. This simply has here multiple nodes here, but still focuses only on their real direct relationship to their real next situated node system. But of course, the beauty comes in if we have an NW-ND system, like we have fast thinking on graphs. And this combines here broader context retrieval with a multi-hop reasoning, leading here now really to the complex reasoning insights that we need for scientific deductions. Let me give you an example. This is from the original literature from this paper. This is a beautiful paper. And the question is, what kind of clothing should I bring along if I head to the area around the Pennsylvania Convention Center in springtime? So here you have now that both if you have a 1W, 1D or NW, 1D GraphRAG, it's simply not finding here the edges. But if you go here to a 1W n-depth GraphRAG system, now we can have thinking, connecting here. There's too much thinking going on, but yeah, it's a good idea to give us here the idea how it works. So we are looking here for the triple. You remember a RAG system, a GraphRAG system is based here on the triplet. So we have Pennsylvania Convention Center is located in the Market East section, is in the city of Pennsylvania. And somewhere we have a link then that humid subtropical climate is the dominant climate in Pennsylvania. So here we find now going step by step, doing too much thinking. We find here enough information to come up with the correct answer. But you know what? It is so much simpler if we go with an NW-ND GraphRAG system, because then we have repositioned here our complete knowledge graph infrastructure here already in communities. And now we've worked with those community. And here you have one community, most relevant one is here. Remember, Triplet Pennsylvania Convention Center is located in Pennsylvania State. And then we have a community where we have already all this information. And then we have, as indicated here, with less thinking, we immediately come here to enough information to also arrive at a correct answer, but in faster, with less complexity, and our chain of reasoning is here significantly reduced because we only go here with relevant community in our reasoning path. And all the other nodes we just delete here for finding an answer. Isn't this beautiful? Here again, if you want to think node on node on node, you have here this one. But imagine this. You just have a graph and you find that we have here 4 communities, and community with potential answer and community with a definite answer. And you can just jump from community and find here and validate here the given fact for your sentence and find a solution to the query. Beautiful. I want to give you a simple example because examples are always good. We have here Philadelphia, the triplet is city of Pennsylvania, and then we have Pennsylvania, climate, humid, subtropical. I don't know if this is a correct statement, but never mind, it's just a demonstration. So to input this structure now into our LLMs, it simply needs to be converted from a triplet structure to a text format structure. And let's say we do this with graph to text. And if you do this, you see immediately we have now a sentence that we can use as an input to our LLM. Philadelphia, located in the state of Pennsylvania, features here humid subtropical climate. No idea if this is correct, but who cares? This is just a demonstration of the transformation process. Great! Okay, I think we are coming close to an end of this video, but let's just summarize what we achieved. We started with 2 innovations, with 2 preprint here on AI research that were completely uncorrelated. The authors didn't know about each other, but reading them today, I think they really go together. Because we need here for our AI system to handle complexity, both in the data and in the decision making. And if you put them together, they create here really a vision of AI that can reason deeply, act strategically, and most important, adapt dynamically to the environment. So we reached our goal. We improved the accuracy of LLMs in our complex task. Isn't this nice? Again, this reasoning community by community is reducing the complexity for the reasoning process. And our multicolored research master eliminates here the complete simulation step in the classical multicolored research by leveraging here LLM self-evaluation in a clever way to reduce computational cost. Isn't this beautiful? And if you take both paper, if you implement both solutions, you see how a structured approach to a problem can significantly enhance the capability and the performance of large language model. And there you have it. This was the video of today. We were talking about GraphRAG system, the latest technology implementation as published today, filming this video. And we were talking here about new multi-agent system implementation for GraphRAG systems and how we can optimize here the knowledge graph representation for GraphRAG system if we do a defragmentation and a redesign of the complete available knowledge space. If you liked it, hey, why give it not a thumbs up? Why not subscribe? And I see you in my next video.